up to this point in the course, we had a detailed look at a lot of basic concepts. Now we're going to get a bit more advanced, because in this course section, we are going to dive into a concept called pointers. And I'll explain what exactly pointers are and why we have that concept. And I will then also show how we do work with pointers. Because pointers will be very important in later course sections and in even more advanced Go concepts, and therefore it is important to get them out of the way right now and to get a first introduction into this pointers concept. Now, to answer the question what pointers are and why we have them, we first of all need to take a step back. We need to look at how data, values that we work with in our code are being stored. And here, an important thing to notice and keep in mind is that values, so strings, integers, floats, and so on, are stored in memory, in your computer memory. And that's true both for values which we store in variables as well as values which we only use once. So for example, if we create a string in the println function call and we don't store that string in any variable. We only use it once, but still, this is a value, this string is a value, and it is being stored in memory therefore. Now there is a difference between those two cases though. On the left side, if we store a value in a variable, then it's kept around in memory until we don't use that variable anymore. And Go will detect if there is no more code left to execute that doesn't use the variable anymore. And on the right side, of course, we instantly don't need that value anymore. So it's used once, and thereafter Go realizes that this value won't be needed again. And for such unneeded values, which will not be used again in the code, there is a built-in mechanism in Go, which is called the garbage collector, which is a little process automatically executed by Go, which will look for unused values and remove them from memory to free up memory. So that if you have bigger programs that are being executed, you don't slowly run out of memory and you take up a lot of computer memory, but that instead unused values are erased from memory. Now, all of that is taken care of by Go for you. You don't need to actively manage the memory, but you should understand that values are being stored in memory, because that will then also be important for understanding pointers. And for that, to move a bit closer towards understanding pointers, let's take a closer look at what storing in memory actually means. How are values stored in memory? For this, we have two sides. We have our values and possibly the variables that hold those values, and then we have that computer memory. Now you can think of that computer memory as a big space with different storage slots, which each have addresses. Basically, just as you have a couple of buildings in a village or a city, and every building has a clearly defined address, typically made up of the street, the specific number of that building in the street, maybe a postal code, and so on. These are addresses of buildings in a city, and it's the same for computer memory. You have various slots, and every slot has an address. That's how you can think about that. Now, if you then create values, for example, because you store them in variables, but also if you would not store them in variables, so if you would use them only once, as you saw it before, then those values get stored in memory. So every value gets its slot in memory, and what you see here on the right in those boxes are those addresses the computer knows for those storage slots. So now in these storage slots, the values from the left, max and 32, are stored, and these storage slots then each have a unique address, which of course is important to retrieve the stored values. Of course, you can also have storage slots that are not occupied, so you can have empty storage. And typically you will have empty storage because if there is no more empty storage available, you're running out of memory, and that typically means that your computer crashes. Now, in your code, if you store values in variables, the variables know about these addresses. And whenever you then work with a variable somewhere in your code, for example, in a calculation, Go will automatically take that address information and get that value for you. So it's fair to say that we store values in variables because whenever you work with those variables, you will get the values automatically. That's how that works behind the scenes. Now, if we move towards pointers, we still have that idea of storing values in memory and having addresses, but now we have this new concept, pointers. And pointers are in the end just variables that do not store the value itself, but only the address. So they don't go to memory and get the value for you whenever you use them in a calculation, but instead they only store the address and nothing else. The syntax for creating a pointer looks something like that, but we'll see this in action in a second. And in the end, what happens here is that user age will be a pointer, and it looks at age and gets the address of the value stored in age, and then user age only contains that address. And if you would use user age in any calculations, you would not get the value automatically. Instead, you would only get the address. Now, that's the idea behind pointers, and we'll see them in action and write some code very soon. But one very important question that probably came to your mind now is, why do we have pointers? What's the idea behind them? Which advantages do they offer to us? And indeed, pointers do offer various potential advantages over plain values, though I will say right away that it's specific use cases where pointers are important. There's nothing wrong with plain value variables as we use them up to this point in the course. But pointers can offer us various advantages. For example, we can pass them as parameter values to functions. And then if we do that, since we pass the address of a value instead of the value itself, once the function executes, Go does not have to create a copy of the received value, so of the parameter value, but instead it can just use the address itself, and you can use that inside of the function to then get the value from that address. Might sound a bit cryptic right now, but we'll see it in action in this section. Another example, also related to functions, would be that we can pass a pointer to directly manipulate a value stored somewhere in memory from inside the function, so that we don't have to return a value and then store that in the place where the function was called, but we directly manipulate some input value from inside the function. And that can also sometimes be useful. And there are other advantages, but that will become clearer once we dive into other, more advanced concepts in this course. For the moment, let's just get started with the core pointer syntax and play around with them a little bit to understand them a bit better, and then in the next course sections we'll also build up on this knowledge, since then we'll use more and more pointers for specific use cases and problems. Now I am back here in an empty project, and again I'll start by creating a new Go module with the go mod init command. And again I'll use this sudo github address I used before as a module name, and use pointers as a module identifier in the end here. Hit enter, and that now created that go mod file. Now I'll add a pointers.go file in here, and in that file I want to write some pointers related code. For that, of course, we start by still making that our main package, and we still add that main function. We always need to add that if we plan on executing this file. And now in here, let's see how pointers work. For this, I'll start by adding a simple variable, age, which holds a value, 32. And then I'll use the format package, and hence, of course, we need that import to print ln this value, this age value, as we did it many times before. Now, of course, should be needless to say, if we now run this here, if I go run this module, we get 32 in the terminal. Now here, I'll add a pointer. And I'll name it my age by again using that colon equals syntax, since I haven't created that variable before. So I want to create it here in this line, and therefore we still use this syntax. But now I use age, but not like this, but instead we add the ampersand symbol in front of age. That's a special symbol which is picked up by Go, which tells Go to get the address of the value stored in this variable, so of this age variable. And hence, if we now again print something, but this time we print my age, then you see I don't get an error here. But if we open that terminal and run this code, now we get 32 from that first print statement still, but from this second print statement, where I print my age, we get this strange value. And that, of course, looks similar to the values you saw on the slides before. This is the address of the value 32 in memory, because my age is a pointer. And if we hover over it, we see that a pointer type is reflected like this by Go. It's basically an integer, but this asterisk in front of it means that it's a pointer at an integer value. So it's pointing at a place in memory where some integer is stored. That's what this asterisk means. And if you would not use this shortcut here for creating that pointer variable and initializing it in the same step, but you instead would want to do this manually, the syntax for that would look like this. You create a variable my age, and the type now is asterisk int. And then in a second line or in the same line, you could still assign a value as we did it before. By the way, if you remove the ampersand here, we would get an error because we here in line 11 say that my age should hold a pointer at an integer value in memory, whereas in line 12 we would then assign the integer value itself, not the address of that value. And that's invalid. We can't use an integer value in a place where the address of an integer value is expected. And the ampersand symbol here tells Go to go and pick up that address of that value in that variable. So that's how we can create a pointer and work with a pointer. And here I'm getting yellow squiggly lines because I have this unnecessarily complex declaration and initialization code. But I wanted to show this as well to make it very clear how this pointer type looks like. And of course, we don't just have asterisk int, we can also have a pointer at a string value or a float 64 or float 32 value or a rune, and then we would have asterisk string and asterisk rune and so on. But here we happen to point at an integer, so it's asterisk int. However, with that, I'll comment this out and go back to this slightly more concise syntax. So now we have such a pointer. What can we do with it? Well, for example, we can use it to still get the value at which the pointer is pointing. Keep in mind, here in line 14, I'm printing the pointer, and if we run this module, we therefore get the address, because I'm printing the value stored in this variable, and that value is the address of age. Hence, we get the address here. But if I want to print the stored value instead, we can get access to that again with the address here by adding an asterisk in front of this variable. We saw that asterisk before on the type when we created the variable. We can also use it in our code if we have an address and we want to get the value stored in that address. So we have ampersand to get the address of a value, and we have asterisk to get the value stored in an address. So basically to reverse that operation. And therefore now if I save this with the asterisk added here in line 14, if we run this code again, we now get 32 here because we do now get access to the stored value. This process, by the way, is called dereferencing because we're diving into that address and getting that value. We can also not just read values with help of pointers, we can also assign values. So for example here, we could use myAge and store a new value in it. Now here you have to be careful. If you try to do something like that, you will get an error if you want to store 33 in myAge. Why? Because myAge is a pointer. It's not the value itself, it's the address of the value. So in myAge, we are only allowed to store addresses. Now 33 is not an address, it's probably the new value we want to store in that address. But then we can't assign it to a variable that only contains the address. And that's basically the error we get here. We can't store that integer in a place where the address of an integer is expected. As a side note, in other programming languages like C++, for example, you can do something like that, and you can then change the address stored in a pointer like that, but that can also often lead to problems where you accidentally change some address. It can also lead to security issues, and therefore Go does not allow that. But how could we now change the value stored in that address? For this, we again need to dereference our pointer. We can again add an asterisk here, and if we do that, we tell Go that we want to change the value stored in the address stored in myAge. And we want to set the value stored in that address to 33. And therefore, if we then print myAge thereafter again, and I don't mean myAge itself, but we dereference it and we print the value stored in myAge, then if I again run this module, we print 33 here in the end because we changed the value here. By the way, what do you think would happen if we don't just print the dereferenced myAge, but we print age itself? So the variable which we created here at the very beginning. What do you think do we get if we print age here at the bottom of the main function? Well, let's give it a try. If I run this module, we get 33 as well here. And that shouldn't come as a surprise because we're working on one and the same value. We created the variable age, then we got the address of that variable, of that value stored in the variable to be precise, and we stored that address in myAge. And then we used that address to assign a new value to it, so to overwrite the value currently stored in it. And therefore, of course, age now also has that new value, because age and myAge in the end are referring to the same value in memory. The only difference is that myAge only holds the address, and we explicitly need to reach out to the value with help of the asterisk. Whereas age does also know the address, but automatically works with and on the value whenever we use that variable. So here we don't need to explicitly reach out to the value when we work with age. But we are working on the same value stored in the same address in memory in the end. And that's how pointers work. But of course, with this very basic example here, it's still not really clear why we might want to use pointers. After all, pointers are just a bit more complex to work with. We always have to add that asterisk, and there isn't a clear advantage of using pointers, right? Well, this was just an example to understand the general syntax. Now I want to show you what you can do with pointers and with that concept of having the address instead of the value. So let's explore why we might want to use pointers, though I want to say right away that the real good use cases will come a little bit later once we also learned about other important Go features. Nonetheless, let's see an example here right now. let's say we have a function called double here, which takes a number as an input, as a parameter, which is an integer, and which should return an integer. And in that function, we might just return number times 2, which will double the input number. Then, of course, here in my main function, I could create a doubled age variable by calling double and passing age, so not the pointer, but the age variable itself, which stores the value itself, to double. And then thereafter, we can, of course, print doubled age like that. Okay, if we do that, it should not be too surprising that if we run this file, we get 66 as our output in the end, which is simply our current age, 33, before this line times 2. Now, what happens here, if we have a function like this that takes a parameter, is that whenever this function is called and a value is passed as a parameter value, like age here, Go will go ahead and copy that value. So it will create a new entry in memory and store that value in that new entry. So if we before had one place in memory where the age was stored, we now have two places. One for the original age and one for the new age. And we can tell that this is the case if we add a result variable here, in which we store number times 2. And then after doing that, we set number equal to 100. And then here I only return result. If I do that and the number would not be copied, so we would get the address of age and we would work on that same value inside of this function as we work on in the main function, then changing number to 100 should actually ensure that the number we pass in is 100 after we called this function. So if I print my age thereafter, this should be 100 if Go would not create a copy of age inside of this function. So if you would operate on the same value in memory, then age should be 100 here, because we override it here inside of the function. But as you can probably already tell by the way I am phrasing this, if we run this module, we get 33, not 100. Because Go is creating a copy. And it has good reasons for doing that, because this ensures that inside of a function, we can't accidentally change a value defined in some other place of our code. If we call the double function and we pass age to it, we can't accidentally change age from inside this function. We only change the local copy of the provided value, and the original value is not stored. Now, that extra place in memory that is occupied is of course freed up once the function execution finishes, because then this number variable is not being used anymore, because it only exists inside of this function. So then it can be garbage collected. But still, during that function execution, we have that copy. And this is not bad. As I just explained, it is a behavior that makes sense. Now, for numbers, this will also probably never be a problem. But we will soon learn about more complex data structures beyond numbers and strings. More complex data structures that can take up more space in memory. And if such data structures are then copied, we have two big data structures in memory. And depending on the kind of application you're building, that could then actually lead to a lot of memory being occupied just because you're calling a lot of functions. And that can make your program slower. Again, definitely not the case here for a simple number, but for more complex data structures, that is a problem into which we can run. And now that is a scenario where pointers could help us. If in double, we don't expect the value, but instead a pointer at a value, so we expect an address, then Go won't copy that value. So here we can make it clear that we want a pointer by again adding this asterisk in front of the type. Now double wants a pointer at a value instead of the value itself. So when we call double, we no longer can pass in age, which holds the value itself, but we should pass in my age, which holds the address. So which is that pointer? And my age like this, not with an asterisk in front of it, because we don't want to pass in the value, but really the address itself. So that here we get the address of a number in the end. Now, we shouldn't change it, of course, here, and we can't change it, so let's get rid of that dummy line. And we, of course, now also need to dereference it if we want to work with the value. So here, when we derive the result, we need to add an asterisk in front of number to get the actual value stored in that address, so that we can then perform this operation on that value. But now, whenever we call double, we'll not copy that value in memory and occupy new space in memory. Instead, we'll just pass the address into that function, and then in here, we work on the same value as we have it here in the main function. And therefore, if that would be a more complex data structure, we avoid that possibly very expensive, from a memory perspective, this very expensive duplication. Now, if we save this and we run this program again, we get the same results as before, but we have this possible performance gain. Now, that was one of the two advantages, or potential advantages, of pointers. Another advantage could be that we can now edit the original value from inside a function. Before, this was not possible because we got a brand new copy. And as we saw a couple of minutes ago, if we tried to change that, if we tried to change it to 100, that had no effect on the original value. Well, now, since we get the address, we can, of course, change the original value. Here, I could now reach out to the value stored in number by adding the asterisk at the beginning and set this to 100. If we do this and we now run this module again, we get 100 here at the very bottom for this print line statement here because we did change the original value because we got its address here. And through that address, we can access that original value from inside this function. Now, sometimes this can lead to horrible bugs and you want to avoid it. But sometimes you also have functions that should indeed manipulate the original value. Again, it's most useful if you have more complex data structures which you might want to manipulate from inside functions. This here, of course, is just a dummy example which has no real purpose. But with that, you still hopefully get an idea of what pointers are and what you can do with them. Now, throughout the rest of the course, where we will now explore more advanced features and more complex data structures, it will also become more obvious when and why you might want to use pointers. You definitely don't need them if you only work with simple integers or strings, as we're doing it here. But now we got the foundation to dive in deeper.